Okay guys, welcome. So in the last video, you would have looked at a generalized process of how we go about proving in the first place that there exists a root between a particular interval for a continuous function. I would have also shown you guys several different methods that can be applied to actually find the root. For example, in this video, um, we would be looking in particular at the interval bisection method. That will be part one. And in part two, we would be looking at the Newton-Raphson method in another video. But these two methods tend to be the most popular ones used when finding roots. So let's look at the first method, which is essentially called the interval bisection method. Now to do this, I will use an example. So let's just say we are given a function x cubed plus 2x minus 2. And the question is telling you that this function has a root between the interval 0 and 1. Now, because the question already clearly states that the function has a root, we do not need to use the intimate value theorem to prove that a root exists. What the question is asking us to do is actually to find the root, the actual value of the root. Let's just say correct 1 decimal place. And we would be using the bisection method or the interval bisection method in order to work out this question. Now, first of all, in applying this method, you need to carefully be able to identify your function. So a function is given by x cubed plus 2x minus 2. Now, the first thing we want to do, similar to actually testing for roots, is we actually want to find the values of these the function values, when you substitute these values of the intervals. So the first interval value 0, f of 0 will clearly give us -2. And if you were to find f of 1, which is the other value for the interval, you'll get 1 cubed plus 2, that's 3, subtract 2, that's 1. So even if you didn't believe them that there was a root, you can clearly see by the intermediate value theorem, there's a change of sign. So the root does exist for this continuous function. But what is the root? Well, first of all, I'm going to draw a little diagram that's going to help us along the way. Now, essentially, this is what your graph will look like. And we have our interval values that are being tested, 0, and we have 1. So there exists a root between these two values due to the change of sign. But how do we exactly zone in? How do we zone in onto the actual value of that root? Well, using the bisection method, the word bisection, when you think of it, means to actually cut in half. So essentially, that is what the bisection method involves. It involves cutting the given interval in half every time. So if we were to cut this interval precisely into two equal parts, we would find that the value lying at the center is 0.5. So applying the bisection method, our first cut gives us the value of 0.5. So what we are going to do is to find our value of our function at 0.5. Now, a simple substitution will give us this. And that value, when you use your calculator correctly, works out to be 0.875. So let's take note of the signs that we got when we substituted our interval values into our function. When we found f of 0, the value was negative. When we found f of 1, the value was positive. So notice that a root exists between two signs that are opposite from each other. When we substituted the value of 0.5, we got a negative sign. Because a change of sign highlights exactly the region where a root exists, then it must mean that between 0 and 0.5, because these signs are the same, there is no root. So what we are going to do is we are going to further test this region over here between 0.5 and 1, because that change of sign is highlighting to us that a root exists there. Now, once again, using the bisection method, so we applied it the first time, we're going to apply it again. And how do we determine what value we are going to find? Well, because it's the bisection method, we are going to bisect 0.5 and 1 in half. I will draw another diagram. So if you were to use your calculator, 1 plus 0.5, and you found that value in the center, you'd find that to be 0.75. So we are going to find the value of the function at 0.75. That will simply be and that works out to be equal to negative 0.078. So once again, let's zone into our signs. We remember from previously, when you found f of 0.5, we got a negative sign. Now we are finding f of 0.75, sorry, and we are getting a negative value. So we know that the root does not exist in this region. Now, what about 1? F of 1 gave us a positive sign. So because there is a change of sign in the region between 0.75 and 1, that must mean that our root exists in this region. So we are going to further test that region by splitting it again in two. So I'm going to draw another diagram. So we have 0.75, which produces a negative value, and we have 1. Now, the value in between them can be found by adding 1 to 0.75 and dividing by 2. That gives us a value of 0.875. So we need to test to determine what sign this is going to produce. So at f of 0.875, when you do your substitutions correctly, you should get 0.419, which is a positive value. And once again, we are looking for the region where we see a sign change to determine which regions we have to keep bisecting. So there's a sign change between 0.75 and 0.875. So what we are going to do here is we are going to test again the center of this region by bisection. What value are we going to use? Well, let's expand the region. We are testing between 0.75 and between 0.875. The value between that is, if you were to add them, 0.8125. And you want to try to be as exact as possible. So at 0.8125, we would get sorry for the scribbles, but I think you understand that these are just those values that are coming from your substitution here. And this works out to be equal to 0.161. Now we're going to look at any possible sign changes here. So we notice that we're going to get positive value here. At 0.75, we had a negative value, and at 0.875, we had a positive value from previously. So no root exists here, and that must mean that a root exists here. Now, we can keep doing this continuously over and over and over as we try our best to find a value or find the root. But how do we know exactly when to stop? Well, if you go back to the question is asking us to find a value of x. They are asking us to find a value of x. Find a value for the root, which essentially is our x value here. And they wanted the answer correct to 1 decimal place. So all you really need to consider is when I approximate my values, when do I notice that those values are tending towards the same? Now, if you look at 0.875 and then you look at 0.8125, 0.875 kind of approximates a little bit towards 0.9, and then 0.8125 approximates to 0.8. So you might want to continue testing this further between these two regions here. Further testing, I think one more step, would actually lead to another value that's, when it approximates, it goes to closer to 0.8. Let me just get the value here on my calculator. If we were to add 0.75 to 0.8125 and we were to divide by 2, the next value that lies at the center of this region actually is 0.78125. And that value is going to approximate to 0.8. And of course, there's going to be a change in sign. So seeing that as we progress, the values of x are getting closer and closer to 1 decimal place to be 0.8, what we are going to say is that therefore, using this method, we have found that the value of the root comes closer and closer and closer and approaches a value of 0.8. Therefore, our root x must be around approximately 0.8 to 1 decimal place. Of course, you could have gone further and you could have found what the function was at 0.78125. But still, even if you did, the value approximated to one decimal place would still be 0.8. So you want to stop when your approximation narrows off to the same value, at least for the last two. So this is how you would apply the bisection method. It would do you well, I would say, to draw these tiny little helper diagrams, because sometimes students get lost as to how to select their region that needs to be bisected. So I hope you guys are a bit clearer on this topic and how to use this method. And I hope you do not confuse it with the actual IMVT or intermediate value theorem, which is just simply used to prove if there is a root. I thank you very much. And always remember, keep practicing, keep trying, you'll get there.